Hello everyone and welcome to Regression Models in Machine Learning. My name is Sharma and I will be telling you a little bit about regression. So, what is regression? More broadly, what is machine learning? So, as an introduction to machine learning is used in everyday life in things like content recommendation. For example, if you watch a YouTube video that was recommended to you, or a Netflix show that was recommended to you, you're using content recommendation systems, and these are inspired by machine learning. Weather predictions are an example of regression. Spam filters are an example of classification, and these are all under machine learning, as well as demand forecasting and economics. As for example, regulating the production of supply. So if you are the manager of some store and you want to know how much to make, how much supply to make, then you would perhaps use machine learning to forecast your demand and then adjust your production supply accordingly. So the overall definition of machine learning is getting computers to learn to do something without explicitly programming them to do that task. So regression is one sub part of machine learning. Regression is used to forecast or predict future data using past data or historical data. For example, weather forecasting would be considered regression. We use the past weather data and we try to find patterns in that past weather data in order to extrapolate that and then predict the weather forecasts for future days. So in general, when you come up with a hypothesis, you come up with a hypothesis of the data, and then you extrapolate that hypothesis to make predictions on future pieces of data. For example, in weather forecasting, we would use use some structures in our weather data and try to extrapolate that in order to predict future values of the weather. And this would, by values of weather, I mean, is it going to rain? What is the temperature, etc. So linear regression is one type of regression, and it's a very, very simple regression. Some math classes view linear regression as simply the line of best fit. So as you can see, we have some data over here. We could fit a straight line through the data, and perhaps it wouldn't be a very good fit for our data, but it's a very, very basic mode of regression, and it's used to teach people about regression. So we'll be covering how to do linear regression. While it's not industrially used very much, it can be a very nice way to introduce people to machine learning. So what we would do is we would extrapolate our hypothesis. So essentially, if this red line over here is our hypothesis, we can extrapolate this hypothesis and continue this line in order to form predictions. So if this was our weather data in terms of temperatures on certain days, we could fit a straight line to it, and we could deduce that the temperature will increase on following days. So how would we evaluate our hypothesis? Once we've created this line, how do we evaluate how good or bad the hypothesis is? Visually, we can see that this does not fit the data very well. It's not very complex, it doesn't show many trends in the data. But what about mathematically? Is there any way that we can compute the error for this hypothesis? Well, it turns out that we can use this thing called the mean squared error. The mean squared error is essentially one way that we use to calculate the error of a hypothesis. So if this is our hypothesis right here, and all of these blue points are the data points that were given, we would calculate the mean squared error by subtracting the prediction from the observed. So we can subtract, for example, this is an observed value of the data, and its corresponding prediction would be over here. So for example, the previous example I was talking about, where we're predicting the temperature, that temperature would the temperature would be along the y-axis, and the day number would be along the x-axis. So right here on day, say, 15, this is our prediction over here, say uh, say 20 degrees Celsius. However, in reality, it's actually much higher than that. And so in order to calculate the error, we can subtract these 2 points from each other, and then we can take the square of that. The square of that would be essentially the distance between that, the positive distance squared. And then we can divide that. We can keep on adding these. So essentially, we add the squared error over here. We add the squared error over here. We add the squared error over here. And remember, the squared error is just the distance from the hypothesis to the actual observed data. And so we can divide that. So we can add all of these squared errors, and then we can actually divide them by the number of predictions, or the number of data points that we have. And so, as I said before, the prediction minus the observed squared actually represents the square distances, the square of the distances added together. Okay, and this is a form of the quantitative error of our hypothesis. This so another name for mean squared error is MSE. That's just an abbreviation. So MSE is is often referred to as our cost function, and it is denoted by the function j. So the j of some hypothesis, so it would be the function, right? So a j of some hypothesis gives us the error. The goal of regression is to minimize the error. So as you can tell, right, if I had a line that just went straight across like this, you can probably imagine that because it's very far from most of the data points, the error might be very high. But as we get to a very nice linear representation of our model, we actually get a very low error. So relatively low error. And so the goal of regression is to minimize that error. And so how does linear regression work? So remember, we are doing linear regression, right? Linear means line. So we're plotting a line. And in general, lines have the form y equals mx plus b, where m is the slope and b is the y-intercept. So essentially, we would be calculating and optimizing these two values, m and b, in order to minimize the error of our hypothesis. So m, as I said, is the slope. M is the slope. So how steep is it? B is the y-intercept. So if I extend my line all the way to the y-axis, where does it intersect? That's what y-intercept means. So we wish to find the numbers m and b that minimize the cost function. The cost function, as I said before, is the error. So obviously you would want to minimize the error of your program. But how is this possible? Well, we have two ways to find m and b, two very general ways. And one is called normal equations, the normal equations, and this involves complex linear algebra. And in general, it's very computationally expensive. And so for that reason, we will not be doing normal equations. Gradient descent, however, is another way to calculate m and b. It is a fancy term for guess and check. It's more computationally efficient in general, and it's applicable to many more advanced problems. We will be using gradient descent in this course. So how does gradient descent work? So gradient descent is another word for guess and check, or trial and error. So if we went back over here, I could take a bunch of random lines and say, um, I could take a horizontal line right here, and I could say, okay, what's the error on that? And then I get a very high error. So I change it a little bit maybe, right? So I become a little bit more steep. So then what is my error? My error is still pretty high, but not as high as before. So I'm going in the right direction. Then I steepen my slope again and again and again. You keep on repeating this. So that is the essential idea behind gradient descent. It's essentially guess and check. So you would start off by randomly defining m and b as we just did, and then you would calculate the error. Then you would calculate the slope of the error. And what does this mean? So if we plot the m and b on the x-axis and the cost on the y-axis, we would find that our graph would look something like this over here. So initially, if we define our m and b to be corresponding to this value right here, then the graph shows us that we will actually get an error right around here. And so essentially what we would try to do is use a little bit of calculus. So deriving this takes a little bit of calculus, but understanding does not. So essentially we would take the tangent line to this, and we would determine, do we need to go up or do we need to go down? And as you can see, in order to minimize the error of the cost function right here, you would want to find the lowest point on this curve. So the lowest point is somewhere around here, and that corresponds to these m and b values. So the gradient essentially, with a little bit of calculus, shows us that if you go in this direction, then you will eventually end up at the optimized values of m and b. So essentially, you calculate the slope of the error, and then based on that slope, you say that in order to minimize our cost function, do I need to go in the left-hand direction or do I need to go in the right-hand direction? Using this gradient, you can actually see that going in the right-hand direction will increase the cost, so you don't want that. You want to decrease the cost. So you would go in the left-hand direction. And then you would try out that and find your error there. Then you would compute the gradient again, and then you would go down one more step, and then one more step, and one more step, until you finally reach an optimal value of m and b. So the plot on the left, I just want to show reiterate that this plot right here is actually the m and b values. That's what w stands for, and j, which is the cost function. And so essentially, this has nothing to do with the original data set that we plotted. This is actually just on W is just a values for m and b, which are sort of determining how our hypothesis would look like, and j is the error. So this is not related. This graph right here is not related to the initial data. It's related more to the cost function. So you might be thinking that, like, how does this work? Like, how do you know that this graph actually looks like this? How do you know it's not something else? Well, more often than not, the plot variable versus cost function. So if I plot variable, our variables, which are m and b, versus the cost function, which is on the y-axis over here, they're called convex, meaning that we can arrive at this thing called the global minimum. So the global minimum would be the lowest point that could ever be achieved on this graph. So that would only occur if our graph looked like this. So more often than not, this is actually the case. This ends up being the case. However, there are other plots as well, other than convex. So convex, remember, on the left-hand side we have convex plots, And this is where you can find the global minimum, the lowest point that can be achieved throughout the entire graph. However, there are also concave plots on the right-hand side over here, and where the algorithm may or may not work. So over here, if I started my gradient descent from up here, I could end up going down here, I could end up going down here, and if this doesn't make sense to you, I recommend you think about it like this. So if I placed a ball over here at my initial theta values, and I let it go, then it would fall over here to the center, to the lowest point on the graph. Okay. However, so over here, if I drop my ball over here, then it would end up going to the center over here, at the lowest point possible. However, if I placed my ball over here, there's no way of telling, will it go in this direction or will it fall in that direction, right? And so most examples, as I said before, are actually just convex. So if it's concave, then it's most likely that your data is not strongly correlated and you're attempting the wrong example. So you would want to double check your data or double check what you're doing is actually correlated to each other. So now we return to gradient descent. So as m or b approaches the minimum, so as we approach the minimum over here, the gradient decreases and approaches 0. So as I said before, this is the gradient right here. This is the gradient or the tangent line. As we go closer and closer to here, so for example, if we're over here, the gradient is actually flat. So if you drew a tangent line, you would find that it's flat. And the slope of that is 0. So the variables m and b are now optimized because this is the lowest that the cost function can go. So if it's at the lowest point, then this is the lowest that the cost function can go. Similar to how we were thinking about the ball rolling down. So if I put the ball over here, once the ball reaches the sweet spot in the middle over here, then you can assume that that area is optimized right there. So as a clarification, I just want to clarify that this is how we will be denoting the data. So the data structure is usually like this. So there's an input and then there's an output. A very simple example, but you can have more inputs, but for now we'll just use one. You would have x1, x2, all the way to xm minus 1, xm, right? And then on the y-axis, you would have data points which are y1, y2, ym minus 1, ym. And so these 2 points correspond to each other. So one of the data points, you would create the data points by taking the x value and its corresponding y value, and then you would plot those as a coordinate point on the plane. So you would plot all of these points, and if you look at the subscripts closely, you can realize that there are actually m different data points that we have. So in general, people denote the number of data points in your data set as m. So using this, we can sort of look at the cost function reiterated, and as well as the gradient descent algorithm. So I'm gonna explain what these theta mean and so like what this all means. Okay, so first there is a convention that we have to look at. So the convention is that b is usually labeled as theta 0. Okay, m is usually labeled as theta 1, and therefore our hypothesis, remember, y equals mx plus b, right? So mx plus b, if you just substitute these two values in, you get theta 1 multiplied by x plus theta 0. So the cost function ends up being a function of both theta 0 and theta 1. Remember, these are just m and b. Oh, sorry, this is b right here, and then this guy is m. And so this is how you would compute the cost function. 1 over 2m, which is, remember, m is the number of items in our data set. And then you would do a sigma from 1 to m, and you would evaluate the hypothesis for an x value. So this is your predicted value right here, and you would subtract it from the observed value, and then you would square that. So what we're doing by doing the sigma is we're iterating through each and every one of the data points, and we're saying, okay, let's take the x value of some data point, and then let's use that to predict the y value. So remember h of theta of x is actually like how we denote our hypothesis. So h theta of x is our hypothesis. So this right here would be our predicted value. And we would subtract that from the observed value and then square that. Remember MSE, mean squared error. So this right here is where we're taking the mean, and this right here is where we're taking the squared error. Okay, and so over here we remember how we first defined our theta value so that the line was horizontal. Then we slowly corrected it to make it optimized. So this is telling us, the gradient descent algorithm tells us how to correct our values. So it says that instead of the whatever theta value you have already, you should replace it with the theta value minus some constant alpha, which we'll call the learning rate, and then times the gradient of your cost function. Remember, we talked about the gradient of the cost function right here and whether to go down or up based on that. So now we multiply that by alpha, and then we subtract that from the original value of theta. And then we have to update all of these thetas simultaneously. So we have to update the value of theta 0 and theta m simultaneously using this gradient descent algorithm. Okay? And in case you don't understand all of what all of this means, that's okay. Just understand the theory behind it. We're essentially computing how badly our our hypothesis is doing, and then we're slowly just correcting it using some calculus approach. And so our hypothesis, the learning rate alpha that I mentioned over here is actually called the learning rate, which I said, and that's equal to your rate of convergence. So essentially, if you go back here, the theta values would go down to the middle over here, right? And then they would converge. What we would say, they would converge over here. So if you see these arrows, the length of these arrows, right? How quickly do we adjust our theta values? Well, that's all dependent on the the learning rate alpha that we have chosen. So alpha determines how quickly we adjust our theta values in order to reach the optimum. So this is the rate of convergence. If we increase the rate of convergence, for example over here, if we increase the rate of convergence, we will go really, really fast downhill. However, if we decrease the rate of convergence, we'll go like very, very, in baby steps, we'll go down here. We'll eventually reach down here, but it'll be a very, very long process. However, you have to make sure that the learning rate alpha is not too big or small. So if it's too big, the algorithm can actually diverge. So for example, if your learning rate alpha is too big, and so essentially if you have your initial weight over here, or initial thetas, I should say, over here, and you compute the gradient to try to adjust it, if your new theta values just decrease, if they just decrease so rapidly, they decrease all the way to here, well, you know you'll have to decrease it, but like by how much do you have to decrease it? If your learning rate alpha is so high that you have to decrease it all the way to here, then the cost function would yield even a higher cost. Even though you were going in the right direction, you actually increased the cost. You should have been going down here, but you overshot. You went all the way up here. Then if you do the gradient descent algorithm again, you might say that, okay, in order to decrease my cost, I actually have to go in this direction down here. But you end up overshooting because your alpha rate is too large. And then it essentially diverges, and you end up with a cost that is very, very, very large. And on the other hand, as I explained, if your alpha rate or learning rate, alpha, is too small, the algorithm can be very, very slow. So if I took baby steps down here, then it would be very slow. However, it would still yield a lower cost each time. You wouldn't overshoot. So throughout the program, actually, you don't have to change the learning rate alpha. Once you set it, as you approach the minimum, the gradient decreases, and therefore, if you see this cost function right here, the gradient actually decreases and approaches 0, and the learning rate alpha times that gradient. Since this guy right here is approaching 0, this whole term is actually approaching 0. So you don't adjust your theta values very, very rapidly. Okay, so now let's talk more about the gradient descent algorithm in general, like putting all of the steps together. So first we would initialize the theta values, remember? So our m and b values, mx plus b, remember? So we would initialize our theta values at random. Usually we choose 0 to be our initial theta values. Then we would compute the cost function and find the error. We would similarly compute the gradients for the theta values and adjust the theta values according to this equation right here. And then we would repeat steps 2 and 3. Just we keep on computing the cost and then calculating the gradient, computing the cost, calculating the gradient, and we keep on doing that over and over again until the theta values converge to some optimal values of theta. And remember, computing the cost function doesn't actually play a part in optimizing our algorithm. It's just to show us how badly or how well our algorithm is doing. It's a mathematical way of for the program to see how well our algorithm is doing. And on the other hand, calculating the gradients is where we actually do like the dirty work, where we adjust the theta values. Okay, so now that we've talked about gradient descent, let's talk about extending gradient descent to more dimensions. So the gradient descent algorithm in more dimensions is, for example, we would use this if we were computing the housing prices. If we were computing housing prices based on number of bedrooms, the square footage of a house, and the number of bathrooms. So if we were taking these three things, the number of bedrooms, the square footage of a house, and the number of bathrooms, and we were trying to predict the housing price. So this is more than one input. Before we only had one input. For example, what is the day number, and we were trying to predict how hot will it be, like what is the temperature on that day. But now we are given all of these different things. We're given the number of bedrooms, the square footage, as well as the number of bathrooms, and we're using all of this to predict the housing price. So it's more than one input. So our hypothesis in linear regression would be like this. Theta 0 plus theta 1 multiplied by x1, right? That's what we originally had, right? And it turns out that you can actually extend this to having theta 2 multiplied by x2. So plus theta 3 plus times some x3. And this is actually the form of some line in some n dimensions. And so over here, this is the number of bedrooms, this is the number of, the square footage of the house, and the number of bathrooms. So essentially, in hindsight, what we're doing is we're setting some theta 0, and we're saying that we're going to adjust the price, adjust the prediction of the price, based on based on the number of bedrooms multiplied by some number. And then we're going to add that to the square footage of the house multiplied by some number. And then we're going to add the number of bathrooms multiplied by some number. So each of these three things has its own weight in determining the housing price. So maybe square footage is a big determinant in some area, um, as opposed to the number of bathrooms. Let's say that x2 is more important than x3. Then the weight for x2 would be greater than the weight for x3. So that's some intuition on how all of this works. So the gradient descent algorithm would be to first initialize the theta values to all be 0. So remember, we have theta 0, theta 1, theta 2, and theta 3. So we have to initialize them to be 0, and then compute the cost function for this hypothesis. So we would compute the hypothesis using the thing on the last slide, so using this right here, and then we would compute the cost function to find the error. And from there, we would calculate the gradients. So remember, the cost function is telling us how are we doing? Are we decreasing the cost, as in are we doing better than before, or are we increasing the error and increasing the cost, as in are we decreasing the improvement of the algorithm? So based on that, we would use the gradient. So we would change the theta values based on the gradients of the theta values, and then we would repeat steps 2 and 3 until we converge our theta values. So if you look at this set of steps, you would realize that this is exactly the same method. Gradient descent algorithm is the same exact method. We're just now incorporating, instead of just theta 1 and theta 2, the theta 0 and theta 1, we're incorporating theta 2 and theta 3 as well. And just a side note, that theta values are actually commonly called weights or parameters. So these would be my parameters. So even with more parameters, this hypothesis right here is actually still just linear. And remember why that is. What is the definition of linear? Even though one of the definitions is that you can plot a line with it, it's actually more like every term over here is just raised to the first power. So x1 is raised to the first power, so is x2 and x3, right? So just like before, it doesn't really capture the structure of the data, even if we just plot a line, right? It's not very complex for a hypothesis. So if we had some exponential curve right here, we would want to find an exponential hypothesis. But this this line right here just fits lines, even though it might be incorporating more features, x's, that it's still just doing something linear. So that's very not very good for us. So let's move on to polynomial regression. What if we were to create a hypothesis that's like a quadratic or a cubic or something with more curves like this right here? So if we were to plot linear regression, we would probably get something along the lines of this line right here that I'm tracing with my mouse. And that's not a very good fit for the data at all, right? The data is more like some sort of polynomial. So how would we model that using some regression technique? Well, so basically what I'm saying is how would we model it to be more like a quadratic or a cubic function, or in general a polynomial with complex curves, rather than just a linear function that's just a line. So what we can do is that we can trick linear regression into computing this sort of polynomial by sneaking in features. So what I mean by that is that instead of just adding theta 1 x1. So remember, like let's consider theta 1, sorry, x1 and x2. For example, the square footage of our house and the number of bedrooms, right? And instead of just having these two guys right here, which is just linear, raised to the first power, remember that, right? We can add features which are theta 3 multiplied by x1 squared. And we can just package this guy, x1 squared, we can just say that that's one feature. Sort of lie to the program and say that that right there is just one feature, and it's a linear feature. And so we can incorporate other quadratic terms, and then we can incorporate other things as well. So more generally, what I'm saying is that if we have some so we have some x1s and x2, right? Instead of just having theta 0 plus x1 times, theta 1 times x1 plus theta 2 times x2, which is linear, we can actually incorporate theta 3 times x1 squared and package this guy as one feature for polynomial regression. And then this right here, we can add theta 4 plus x2 squared, theta 5 times x1 times x2, theta 6 x1 to the power of 3. And we pass these off as just being a linear term, so that we can do the same exact method with linear regression to calculate the optimal values of theta. So these are some kind of features that we could add. We could add x1, then x2, then x1, x2, then x1 squared, then x2 squared, then x1 squared, x2, x1 to the x1 cubed, x2 cubed, x1, x2 cubed, x1, x2 squared. So these are some different features that we can sneak into our linear regression program to compute polynomial regression. What we end up getting for our gradient descent algorithm, which is generalized now, is that we initialize the theta values, of course. Always we initialize them like at 0. And then we compute the hypothesis, and therefore from there we compute the cost function. Find the error, right? To indicate how well our program is doing. Then we calculate the gradients. The gradients being the gradients for the theta values in order to adjust the theta values in the right direction. And as always, we keep on doing these two things, computing the cost and then computing the gradient and adjusting the values of theta. Keep on doing that over and over and over again until the theta values converge. So remember, this is exactly the same algorithm that we did before, the last two times. However, now we compute the hypothesis differently. So as we said on the last slide, this hypothesis is just a tad bit different. We incorporate features such as x2 squared, x1 squared, instead of just these linear terms right here. That's the only difference. Otherwise, it's all the same. However, so in summary, we end up with something like this when we do polynomial regression and trick the machine into doing polynomial regression. However, polynomial regression can actually have some drawbacks. So if we add like a lot of different features, right? So if we add 100 features, right, and we want to compute like quadratic regression, it has somewhere around 10,200 terms in this hypothesis, and that evaluating the hypothesis every single time using all of those 10,201 terms, that is actually very computationally expensive, right? So with a so basically it's computationally expensive on one hand. On the other hand, it with a high enough degree, right? So for example, it can be shown that with a high enough degree, I can actually go through each and every one of these data points and use a polynomial to go through as I'm tracing my mouse over right now. And I go through each and every data point. And so polynomial regression can sometimes do that if the degree is very, very, very high. So if I set a 20th degree polynomial to this data set back here, then it would be very, very precise as long as I ran it for many, many iterations. So essentially what we're saying is that polynomial regression, there is some such thing as too good. In other words, it may be so good at predicting or at synchronizing with the training values of the data set that when we try to extrapolate our hypothesis in order to predict new values of the data, we end up failing at generalizing our trend. So if we have such a tight fit to our data, we end up doing this thing called overfitting. And in overfitting, you go through every single data point, and it's very, very exact to the data, and therefore when we try to generalize our hypothesis to use it to predict new examples and extrapolate our hypothesis, we end up not being able to do that because it's so adept to the training set. And in order to fix overfitting, we can use we can use less features. Of course, we can use a lower degree, right? Because as I said, like a 20th degree polynomial might be very, very, first of all, computationally expensive, but also it might be very, very exact to our data. However, if we implemented something like a third degree polynomial, that wouldn't be as bad. And we can also do this thing called regularization, in which we penalize the theta values. And I'll talk about more about that in a second. So this is overfitting in more detail. So if we have linear regression, if we have this data set right here, and we have linear regression, linear regression won't be able to come up with something very good for this. Even though it tries its best, it's still just a line, right? So this is called underfitting our data. Our hypothesis is not complex enough to find the actual trends in the data. And now there is also the good fit, like the sweet spot in the middle, where you have a good fit in a robust model, where you have a very nice model over here where it's able to pick up the general trend of the data and generalize to new values. And then there's overfitting. Overfitting, as I talked about, goes through every single one of the data points, goes out of its way to reach every single one of the data points. And if we try to evaluate the hypothesis, say if we try to evaluate the hypothesis for here, so for this time, the value would be right here. But realistically, we would expect it to be somewhere maybe around there. So it's not very good at generalizing to new examples, in summary. In order to fix overfitting, we do this thing called regularization. In regularization, we change our cost function. So we penalize the theta values, except for, of course, for theta 0. So if this is our hypothesis over here, we penalize theta 0. We penalize everything except for theta 0, all theta values except for theta 0. But how do we do that? We add, at the end of our cost function, we add the square of the theta values. So, as you can see, this is our normal cost function right here on the left-hand side. On the right-hand side, we've added a term. There's a lambda, and then there's this term right here, okay? And so the lambda we'll talk about shortly, but this term right here, this is essentially saying that for all theta values, to compute the square of that theta value. So you would take the theta value and you would square it, whatever it is, and then you would add that to another square of another theta value, and then you would essentially square all the theta values and add them together, and you would multiply that by some constant lambda. And essentially, we'll talk about lambda in a second, but essentially, if you add the square of all the theta values to your cost function, your cost function is undoubtedly going to get bigger as the theta values become bigger. So for example, if I set my theta, one of the thetas, to 10 million, then my cost function would become 10 million squared plus some other squares, right? But that 10 million is so huge, but we want to minimize this cost function right here. So what you end up doing, the program ends up minimizing these theta values in order to minimize this term over here on the right. Okay? It tries to minimize the theta values as much as possible. And what this does is that, for example, in this scenario right here, it tries to minimize these theta values, all of these theta values, so that they're as close to 0 as possible, while also giving a good fit for our data. So that ensures that, for example, theta 6, which is a cubic term, so it's representing a cubic term, it stays as close to 0 as possible. This means that it's not able to incorporate as many degrees as it wants. So if I had a 20th degree polynomial, then even though I have a 20th degree polynomial, and if I used regularization, the 20th degree term should actually be very, very, very small. And this ensures that I don't overfit my data. And so high a lambda value, so I'm going to talk about the lambda value now, how that affects our data. So by default, you can think of lambda to be 0. So lambda being 0 just cancels out this term over here, and you're just left with your original cost function. So once you actually make the lambda something other than 0, if you make the lambda value high, you ensure that all of these, so essentially if you make the lambda value high, you're adding the square of all of these theta values together, and then you're multiplying that by a huge number, right? And then essentially that causes the cost function to decrease the theta values more and more and more. Even if it means increasing this, even if it means increasing this guy over here. So as you increase the lambda value, you end up having more regularization, right? So you bring them closer and closer and closer to 0, but you end up having this higher bias. So I'll talk about bias in a second. Actually, let me talk about it right now. So bias is what we would call underfitting the data. Underfitting the data and bias is the same thing. And a small lambda value would mean less regularization. So in our case of a 20th degree polynomial, right, then if I have a very, very small lambda value, our program doesn't really care about making this term very large. It only cares about minimizing this cost function right here, because if your lambda value is very small, then essentially this term doesn't really matter. So you end up having the same problem that you were already having, which is overfitting your data. And another word for this is variance. So overfitting is the same thing as variance. Okay, so now that we know a little bit about linear regression, polynomial regression, and regularization, I want to tell you more regression explorations that will not be covered today. So the ARIMA model is very similar to linear regression or polynomial regression, and it's a type of regression model that recognizes seasonal trends in the data. So this is one regression model. And then there's another regression model called the random forest algorithm, and it's very, very popular. It essentially how it works is the random forest algorithm splits the data set. So if you have a certain data set, it splits the data set into multiple different data sets. So essentially, it just takes a few random values from the data set and puts it in one data set here. Takes a few random values from the data set and puts it here, and keeps on making more and more subsets from your original data set. Um, and and essentially, what happens is you perform regression on on each of those subsets of data, and essentially it takes the mean of those. It takes the mean of all of those predictions, and this is similar to, for example, voting. Okay, so I already have multiple regressions which are working to extrapolate the data, find the hypothesis, and sort of predict future values, right? And I have all of these different um, um, regression models, and now to make my final forecast, what I do is I take the mean from all of these different estimators. So it's similar to voting. So these are two um, very common regression algorithms. And then um, going even further back into this thing called supervised learning. So regression is actually under supervised learning. And so supervised learning is when you're given you're given a data set which has data that is labeled. And this means that you're given you're given that on day 1 you had 20 degrees Celsius, on day 2 you had 24 degrees Celsius, on day 3 you had 23 degrees Celsius, something like that, right? And so your data is labeled. You have both the x values and the y values. And so the things that would fall under this are regression, which we introduced today, and classification, which is essentially like determining whether or not it will rain tomorrow. So you have a discrete set of answers, yes and no, right? Will it rain tomorrow? Yes or no. And you could use past values of data to predict this. So if it usually rains on like in the winter, and it's the winter right now, then it will likely it's more likely to rain. And you're given all that data that you're given the x values as well as whether or not it rained, so the y values as well. So you're given label data, and that's why it's supervised learning. And so these would be different sort of uh, classifiers. So logistic regression, while the name says regression, it's actually not regression. It's classification, and these two are actually very different. And then there are SVMs, support vector machines. And these are two different ways people can use to classify different things. Stepping even further back, we gaze at machine learning as a whole. So we have three main subsets of machine learning, and the third subset can be applied to each of them. The first one is supervised learning, which we already talked about. The second one is unsupervised learning. For example, you're given unlabeled data. So for example, this guy on the left-hand side, and you are asked to find structure in the data in order to be able to label the data. So you implement some algorithms such as k-means clustering, and then you end up sort of classifying your data and into these three regions over here. And applications of clustering would be, for example, audio cleaning. So if there are multiple people speaking at once, and you would want to clean the audio so that you can take the audio from the first person who's speaking and the audio from the second person who's speaking, you can, that's unlabeled. You're not given the answer. You're not given whether or not, like if what person one is saying, what person two is saying. You're not given any of that. You're just You're just given the two audio recordings and you're asked to clean the audio. So that would be unsupervised learning. And so then the final topic is neural networks. So this uh, sort of application of machine learning is used. So essentially, we take inspiration from the way the human brain works, and we try to use that for classification, such as image recognition. Image recognition can be done using neural networks, as well as many regression techniques and classification techniques. They can all be used. You can use neural networks for that, and they can come up like so. This is an example of a neural network right here. That's what it would look like. And using a neural network, you can actually come up with extremely complex hypotheses. So today we talked about polynomial regression, coming up with complex hypotheses, more complex hypotheses um, than linear regression. But we can also implement neural networks, and neural networks are very complex as well. And a lot of the things that we did apply to neural networks as well. So that's a bit about machine learning and regression. And now a little bit about me. So my name is Jay Sharma. Once again, I am a rising 10th grader, and I'm teaching another class on AMC8 preparation. It's those classes. They are. You can contact me at jsharmaus@gmail.com, and you can ask me if you are interested in joining. And essentially, I am by myself. I'm studying math and machine learning. So, hope you had fun today, uncovering the secrets of regression and machine learning. And hopefully, this will give you a start on your career as a data scientist or a person doing machine learning, maybe just for fun, right? Just to learn about the subject. Hopefully, you had fun. Thanks for watching, and these are my references.